All right, it's week 4 Thursday, and we're I guess moving right along here, and we're going to cover more material. So now we are going to look at chapters 9 and 10 in the textbook, and I think we can cover both chapters today, no problem. And chapters 9 and 10 are all about kind of hypothesis testing and statistical inference for categorical variables. So, pretty much so far, everything we've been working on has, involved, a numeric variable where we're comparing things like the mean or just the distribution of values, is this value bigger than the other value, or is the mean of this group bigger than the mean of that group? And now we want to talk about a categorical variable. So a categorical variable, we don't have these quantities. We're not talking about, is one thing bigger than another thing, but we're just kind of comparing categories. So it could be something like, we're looking at the example that we'll look at will be, we're looking at some flowers or something, and some are going to be red and some are going to be white and some are going to be pink and things like that. And we're going to compare kind of the counts of these flowers, or the counts of the different categories, or the proportions of our different categories. So first we'll start off with a confidence interval. All right, and so when we look at a kind of a proportion, we can we can create a confidence interval for the proportion that, say, exists in a population. Okay, and so this confidence interval stuff works best if there's really just kind of like one category that you're interested in, and that category will kind of split the population into basically things that belong in that category and things that don't. It's going to kind of dichotomize the category. So either it answers yes, it belongs in the category, or not, right? So it could just be, does someone blank, right? Does somebody do this one activity, or does somebody fit in this one category, or whatever it is? And the answer is just going to be yes or no. Okay, this is not going to be something where we have multiple categories. The confidence interval is really just, what proportion of people are blank, whatever it is. Okay, so for example, we could say, we can talk about, what proportion of people are diabetic, have diabetes. And so to talk about diabetes, a lot of times the classification is, that we'll look at this blood sugar test. We'll look at the A1C level. And if A1C level is over 6.5, that person might be classified as being diabetic. Okay, and so we'll just say what proportion of people in the general population have an A1C level over 6.5, and meaning they would be classified as being diabetic. And sometimes the medical guidelines will change. I think a couple of years ago they changed the guidelines for what it meant to have high blood pressure, hypertension, and I think they changed it to anybody who's over I forget 100, 120 or something like that, 130 or something could be considered at least hypertension stage 1 or something. And so you could ask the question, what proportion of people have hypertension stage 1, which will be their systolic blood pressure is over 130 or something. I don't know the exact number, something around that, right? It could be another question could be something like, what proportion of students voted in the last election? Okay, and so there you've defined your population. It's going to be the population of students, and then the kind of the category of interest will be people who voted in the last election. Okay, or what proportion of Californians drive a hybrid or an electric vehicle? And that's going to be some proportion there, right? And so here again, as always, the population is assumed to be this large entity that we cannot observe directly, and within that population, some proportion belong to a particular category. And the symbol that we use to represent the proportion is the letter P for proportion. And so the confidence interval, we're going to create basically an interval of values for what could be considered plausible values for the population proportion P. Okay. And so, one thing that's a little bit different about confidence intervals for proportions is that you have this hard limit of 0 at the minimum and 1 at the maximum, right? So, your confidence interval, if you do the calculations, sometimes it can end up being negative, sometimes it can end up being over 1, but obviously when you create your confidence interval, it has to, it can't go lower than 0 and it can't go above 1 either. And so, when we create a confidence interval, first we're going to start off with the proportion that exists in our sample proportion. And generally the observed proportion is just going to be the count of yeses, y, divided by your sample size, right? You just do y over n, and that's going to be your p hat. So if you took a sample of 50 people and 50 students, and let's say 30 of them voted in the last election, your proportion would be 30 divided by 50, and that would be, your p hat would be 60%, right? 30 divided by 50. Okay. And I would say, a lot of textbooks just use this p hat, the sample proportion or your observed proportion, as kind of the value, the central value in the confidence interval that goes in the middle of the confidence interval. We go plus or minus some margin of error, et cetera, et cetera. Okay. Our textbook does something a little bit different, and it uses what's called the Wilson adjusted proportion. And what the Wilson adjusted proportion does is it adds 2 to the numerator and it adds 4 to the denominator. So instead of if your data is 30 divided by 50, or 30 out of 50, fit some category, your p tilde, p squiggle, whatever you want to call this, your Wilson adjusted proportion, you're going to add 2 to the numerator, you get 32, and you'll add 4 to the denominator, and you'll divide by 54. And what this does is it just kind of, adjusts or, fudges the number a little bit. Its effect is most pronounced when you have proportions that are very close to 0 or proportions that are very close to 1. So for example, perhaps you want to know, what proportion of people, test positive for a certain disease, right? And this might be a very rare disease, okay? A rare disease that, only affects, very few people. And so it's possible that you survey, say, 200 people, all right? And you get a sample of 200 people, and in that sample, 0 people tested positive for the disease, okay? So your sample proportion would be 0 divided by 200, your p hat would just be 0. Now, if your p hat is 0, that causes some problems, okay? Your standard error becomes 0, and basically you can't create a confidence interval, you can't really do inference. And so by adding 2 and adding to the numerator and 4 to the denominator, we prevent ourselves from getting a proportion of 0. So if we had 0 out of 200, we would add 2 to the numerator, and it would become 4 to the denominator, and it would become 2 divided by 204, and we get, adjusted proportion something around 1%, a little bit less than that. And similarly, the opposite would also be true. If you take a sample and of let's say 500 people, and all 500 people responded yes. So, it could be something like, I don't know, something where, 500 out of 500 people would say yes, but, again, it could be, some very common condition or something. And in that case, your p tilde would be your p hat would be 1. And again, if you get a proportion of 1 or 0, it causes issues. And so if you have 500 out of 500, your adjusted proportion will become 502 divided by 504. And so it becomes just a little bit less than a proportion of 1, something like 99 point something %. Okay. And so, yeah, question says, when we do problems on the exams, do you want us to use the adjusted p hat? So I would want you to use this Wilson adjusted proportion. And I would specify that, on a quiz, I'll say, create a confidence interval using the Wilson adjusted proportion or something like that. So I would clearly specify that this is the value that you should use, okay? And again, if you pick up another textbook, you might see this, okay? Our textbook does this, and again, the purpose of using this adjusted proportion is that it avoids issues where you might have a proportion of 0 or a proportion of 1, okay? With this adjusted proportion, you'll never get a proportion of 0 and you'll never get a proportion of 1, okay? And so once you calculate your adjusted proportion, p tilde, you can get your confidence interval. The resultant confidence interval is just p tilde plus or minus the margin of error. Your margin of error is going to be 1.96 times the standard error, okay? The 1.96 comes from basically the normal distribution where your middle 95% lie, the middle 95%. To get that, you'd go plus or minus 1.96 on the z table. And then this is just the formula for the standard error. So the square root of p tilde times 1 minus p tilde divided by n plus 4. That's going to be the formula for the standard error, okay? As far as our class goes, we're just going to stick with the 95% confidence interval. You can read the textbook, which covers, what are you supposed to do if you want to do a 90% confidence interval or a 99% confidence interval. And to change the level of confidence level, it's not as simple as just switching 1.96 to something else, but you actually have to adjust the way you calculate your Wilson adjusted proportion. So it just becomes a little bit more complicated. It's not too hard, and it's covered, I think quite well in the textbook, but I'm not going to test you on that. Okay, so as far as this class goes, if we're talking about a confidence interval for proportion, it's going to be a 95% confidence interval. All right, and then so basically all of the ideas for a confidence interval will apply here, right? So here I made up this thing. I have no idea. I don't think these numbers are true, but let's just say you survey. I'm sure this number is much lower, but let's say you take a survey of 100 randomly selected people and you ask, how many of you have a Netflix subscription? And, that's significantly different from how many of you have access to Netflix, just because I think people share their accounts and stuff. But we'll just say 30 people out of 100 said they pay for Netflix and things like that. And so what can we say about the proportion in the population that subscribe to Netflix? Okay, and so what we'll do is we'll make a 95% confidence interval for P using the Wilson adjusted proportion. So we start off by calculating our P tilde. And so we're going to add 2 to the numerator. So we're going to have 30 plus 2, and we're going to add 4 to the denominator. So it'll be 32 divided by 104. So that's going to be our P tilde right here. So that becomes just a little bit over 30%, something close to 31% or 30.77, 0.3077, okay? And now I'm just gonna plug in the values that I have into the confidence interval formula. So I think this is rather straightforward. You just plug in 0.3077 for P tilde. Every place you see P tilde, we're gonna plug in 0.3077, and then N is 100. And so we're going to have 0.3077 plus or minus 1.96 times this whole thing. And I think this whole thing computes out to be something just under 9%, like 8.08 something. Okay. So question, is P tilde the same thing as P hat? It's a tiny bit different, okay? P hat would just be Y over N. 30 over 100, P hat would be 30%, that's your sample proportion. P tilde is the adjusted proportion, and it's a little squiggle over the P, so it is something different, okay? So P tilde and P hat are not the same. They're similar values, but they're not exactly the same. P hat, in our case, is 30 out of 100, 30%, and this one is just a little bit different, it's closer to 31%. Okay. All right. So anyway, you do your calculations, you get these numbers, and now we say, I am 95% confident that the proportion of Netflix subscribers in the population, because again, we're always making a statement about the population, never about a sample, never about future samples, never about individuals or anything like that. We're talking about the population proportion, and we're saying I'm 95% confident it's between 21.9% and 39.64%. So something between 22 and 40%, something around there. Okay. All right. So I think we've become accustomed to these questions by now. So I just have them thrown up here and we can go through them. But if you want to spend more time on the slide, we can. But if we say, do we have evidence that the proportion P in the population, right? The population proportion P, is that different from 20%? What we do is we look for, is 20% within my interval? And the answer is it's not inside my interval. And therefore, I do have evidence that it is different from 20%, right? So do we have evidence that the proportion is different from 20%? The answer is yes. 20% is not between the ends of the interval. It's not a plausible value. We have evidence that it is different from 20%. Okay, do we have evidence that the proportion is different from 25%? Okay, and so 25% is inside the interval. Okay, so it would be considered a plausible value. So we cannot reject 25% as a possibility, right? So we're going to say we do not have evidence, or we cannot say that we have evidence that the proportion is different from 25%. Okay, and going along with that, do we have evidence that the proportion is equal to 25%? Okay, so saying that we don't have evidence that it's different is not the same thing that we have evidence that it is equal. Confidence intervals can only kind of provide a range of plausible values, and we can never say the confidence interval provides evidence that the proportion is exactly equal to some particular number. That's never our business. So, basically any value between 21.9 and 39.64 is plausible. We'll leave it at that. And that's all we can say. We can't say it's definitely equal to 25% or it's definitely equal to 26% or anything like that. Okay, how do we feel about all of this? All of this confidence interval stuff. Now we're dealing with proportions. Okay, great. Thank you for your thumbs up. Let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter D. D as in dog. D as in dog is your first view quiz answer for week 4, Thursday, week 4. And this is end of 4th week. We're, I guess, 2/3 of the way through the quarter. This would be something around the end of 6th week, 7th week, something like that. D as in dog, dog. There we go. Okay. All right. Let's move on to our next topic, which would be the chi-squared goodness of fit test. So we're going to see 2 chi-squared tests. We've got the goodness of fit, and then later on we have the chi-squared test for independence. Okay, so it's chi, C-H-I is pronounced chi, and that's because it's from the Greek alphabet chi, and it looks like an X, but again, it's pronounced chi. Now, if this were something, East Asian something, you would pronounce CHI as chi, and it's, like the idea of like energies and stuff like that. But coming from Greek alphabet, it's chi. And so we have the chi-squared test, and we call it the goodness of fit test because it is going to measure how well the data fit an expected set of proportions, right? So how good is the fit between what we observe and what we expect? And we actually don't, this is kind of like this little lexical hole in our English language, you can add ness to a lot of nouns or a lot of kind of adjectives to kind of create its noun form, right? Like you have someone is happy and you have happiness, and we want to measure someone's happiness or something like this, right? And so we want to measure how good something is or how well this thing fits, but we call this the goodness or the wellness if it wouldn't work, goodness if it, yeah, goodness is a little bit strange because it's like a virtue, right? Okay, but anyway, basically the way it's going to work is your data is going to be counts of different categories, right? You have a categorical variable with different kind of categories, and you're going to have counts of how many you observed in each category. And meanwhile, your hypothesis is going to be a set of proportions for the different categories, okay? And you're going to write out your hypothesis as a list of expected proportions. All right, and so I did not study biology, but I do remember this from like high school bio. You had like a Panette Square, right? And so you have these, these alleles and whatever, you got the big A and the little a for dominant and recessive genes and things like that. And so if we have two kind of parents, each with a big A and little a, and they have progeny, their offspring, would we expect, if this model were correct, right? If this were correct, we would expect 25% to have big A. We would expect 50% to have big A, little a, and we would expect 25% to be little a, right? And the dominant trait would show up in 3/4, and the recessive trait would show up in 1/4. But if we were able to kind of detect these things, we would expect half of them to be big A, little a, a quarter to be little a, and so on and so forth. So the null hypothesis we write out as basically a list of the proportions that we would expect if whatever theory we had was true, right? So if this model applied, if we think this genetic thing or this trait follows this genetic model or something, and if this were actually true, then when we investigate our specimens and things like this, these are the proportions that we would expect. We're expecting 25% this, 50% this, 25% this, okay? And so that's our null hypothesis. It's basically a list of categories and our expected proportions for each category. The alternative hypothesis is very simple. It's just at least one of those proportions is wrong. Okay, at least one of those proportions is wrong. And if you have more than two categories, the alternative hypothesis is always non-directional. Okay, if you only have two categories, you can have a directional hypothesis. You can basically say, the proportion of yes is even higher, and that means if the yes is higher, then that means the no's have to be lower, okay? Or if the yeses are lower, then the no's have to be higher. But if you have three categories, right, categories 1, 2, and 3, you can say, if you try to make it directional and say 1 is too big, then the question is, okay, well, if 1 is too big, then does that mean 2 is too small, or is 3 too small, or are both 2 and 3 too small? And it gets a little bit difficult to kind of pinpoint exactly what adjustments you need to make, right? And it's even more complicated if you have more than 3 categories. If you have 5 categories and you want to say, category D is too big, then which categories do you have to kind of shrink in order to kind of compensate, right? Because everything has to add up to 1. And so if one of them is too big or too small, you have to kind of make up for it in the other categories. But exactly how you're going to do that is not clear. So as far as having more than 2 categories, you just have to, all you can really say is that at least one of the proportions is wrong, but you're not allowed to really specify which one. If you do want to specify that it is this one category and it's too big or it's too small, then you have to kind of basically dichotomize the variable into saying, you have category D, which is of interest, and you're going to say, I think it's too big in our hypothesis, our alternative hypothesis is that it has to be something bigger. And and that means everything that's not category D, and you're going to basically dichotomize your variable into just category D versus everything else. Okay, even if there's like 5 original categories, you have to kind of turn it into just 2 categories if you want to have a directional alternative. All right, but as far as we're going to concern ourselves right here, we're going to just leave it as a non-directional alternative. At least one of the proportions is wrong. We don't know which one. We're just curious if one of these things are wrong. And let's say we go and we gather data. Okay, and this is our data. We've got 200 observations, I believe. We have 45 big A, 106 big A, little a, and 49 little a, little a. Okay. All right. And so we have a total of 200 observations. Okay. And so what we want to do is we want to compare what we observed, which was 45, 106, and 49. That's what we observed. And the question is, well, what kind of counts would we get if the null hypothesis were true, right? What kind of counts would I expect to get if the null hypothesis were true? So if I told you we had a total of 200 observations, if these proportions were true, we would expect 1/4, 25% of 200 or 50 to be big A. We would expect half of 200 to be big A, little a. So we would expect half or 100 of them to be big A, little a. And we would expect 1/4 to be little a, little a. And so my expected proportions would be, we would take the total count, in our case, 200 observations, and we're going to multiply it by the proportions that are listed in the null hypothesis. And so my expected counts are going to be 50, 100, and 50 for categories big A, little a, and little a, respectively. Okay. All right, is that okay as far as getting my expected counts based on how many observations total I have and the proportions that we listed in our null hypothesis? Okay, so I hope that's all right. Okay, and so this is our expected counts, and notationally we would say it's going to be n times p sub j. P sub j is the proportion of category j in the null hypothesis, and n is the total count of your observations. So it's n times p sub category AA, p sub category A, little a, big A, little a, so on and so forth. So that is that's how we get our expected counts. And then what we're going to do is we're going to calculate our test statistic. And so what we do is we say, okay, what's the difference between what we observed and what we expected to get? And let's see what's happening here. Okay, so again, our observed and expected. And then our chi-squared statistic is going to be the sum. And we're going to do this calculation: observed minus expected squared divided by expected. We're going to do this for basically all categories, and we're going to sum this up. Okay. And so let me just kind of list off what we saw. And so we have 45, 106, 49. We observed 45, 106, 49, and we're expecting 50, 100, and 50. Okay, and so the question is, I didn't get exactly what I expected. Okay, I'm expecting 50 and I got 45. Is that difference, is that a big deal or not? Okay, and so our chi-squared statistic, we're going to take these differences between the observed 45, we're going to subtract off what we expected to see. We're going to take that difference. Okay, I got 5 less than what I expected. Okay, and we're going to divide by the expected. So we square those differences, divide by the expected, and we do this for all 3 categories. So I expected 100 and I got 106. I got 6 more than what I expected. Is that problematic, right? Here I expected 50 and I got 49. So that doesn't seem like a big deal, right? That seems like I got pretty close to what I should have gotten. The question is, are these other things, a problem or not? So 45 minus 50, I get 25 over 50. I get 36 over 100 plus 1 over 50. What is this? 50 plus 36 plus 2. So 88 over 100. So not even 1. I get a chi-squared statistic of 0.88, I believe. Okay. So this is the work to get my chi-squared statistic. Okay. And what we're going to do, this is my test statistic. This is my chi-squared value. And we're going to go to the table. We go to a reference table. And the degrees of freedom we're going to use is going to be the number of categories minus 1. So I have 3 categories, big A, big A, big A, little a, little a, little a. 3 categories, so I'm going to have 2 degrees of freedom. We're going to go to our chi-squared table with 2 degrees of freedom. All right, what do I do in my table? Something's going, oh, here we go. Okay. So I need chi-squared table. Table 9, critical values of the chi-square distribution. Okay. All right, so we're going to go to 2 degrees of freedom. And well, the first value I see is 3.22. Okay, the chi-squared table, the chi-squared distribution is kind of this funny looking distribution. It only has positive values. Okay, it's actually the distribution of, if you take a normal random variable and you were to square it, what kind of values would you get? So on the low end, you have 0. And basically, the farther and farther you get away, right? So what we're saying is that if you go to 3.22, this tail area is 20%. If you go farther out, 4.61, the tail area is 10%, and so on and so forth, at least for 2 degrees of freedom. If we go further out to 5.99, then this tail area is 0.05, and so on and so forth. And this tail goes on for a long time, and you have to go pretty far out, 18.42 or something, if you want your tail area to be quite small, 0.0001 or something. Okay, but anyway, our chi-squared value is 0.88. All right, so that means we were to draw a line like 0.88, and if I were to draw this line, and if I were to shade everything to the right of this, okay, we're gonna have a huge p-value, right? I don't know the exact p-value, but the p-value, whatever it is, it's gonna be quite big. It's gonna certainly be bigger than 20%. Okay. Is that okay? The arrival at our p-value. Now, again, all of these tables, they all have like different things going on. So you have to just kind of read the heading at the table. And so it says the column headings are non-directional p-values, right? And it says if the alternative is directional, and it says which is only possible when degrees of freedom is 1, then directional p-values are found by dividing the column headings in half. So you can take the column headings and divide them by 2. And that would give you your directional p-values. But overall, we have a non-directional test. We're going to get our non-directional p-value. Our non-directional p-value is going to be over 20%. We don't have the exact value, but we just know it's over 20%. So I think that's what I wrote here. We have 3 categories. Our degrees of freedom is 2. We look up test statistic 0.88 with 2 degrees of freedom. And so our tail probability is greater than 20%. If we have a significance level of 5%, if we choose alpha equal to 5%, our p-value is greater than that, we would choose not to reject our null hypothesis. And we would conclude that our observed data do not provide evidence that the proportions listed in the null hypothesis are wrong. So when you go out and you count the things and you get 40, whatever, 46, 45, 106, and 49 or something like that, it's not, there's no discrepancy between what we observed and what we're expecting, right? So you can use the chi-squared goodness of fit test for things like testing to see if a die is fair, right? So if you roll a die, you're expecting each of the 6 sides to show up with equal probability. So now you have 6 categories, and you could roll the die, say 1,000 times or something like that. And you can say, well, how many times did I get the number 1? How many times did I get the number 2? How many times did I get the number 3? And if you roll it 1,000 times, you'd expect, around 167 of each face to show, each face to show up around 167 times. Of course, it's not going to be exactly that because of randomness. And, let's say one of the faces shows up like 220 times. Is that a problem, or is that within randomness, right? And you can do a chi-squared test there, okay? Let's check this out. This is an example from the textbook, and I thought the experiment was quite clever, and the findings were quite interesting. And so I'm going to just read this straight from the textbook. And so the question that the researchers start off with was, can people who are close to death postpone dying until after a symbolically meaningful occasion? And so the researchers studied death from natural causes among elderly Chinese women, which they defined as Chinese women over age 75 living in California. They chose to study the time around the Harvest Moon Festival because, one, the date of the traditional Chinese festival changes somewhat from year to year, making it less likely that a time of year effect would be confounded with the effect that they were studying. And 2, it is a festival in which the role of the oldest woman in the family is very important. So it said previous research had suggested that there might be a decrease in the mortality rate among elderly Chinese women immediately prior to the festival, with a corresponding increase afterwards. The researchers found that over a period of several years, there were 33 deaths in the group in the week preceding the Harvest Moon Festival and 70 deaths in the week following the festival. How strongly does this support the interpretation that people can possibly prolong life until a symbolically meaningful event? Okay, so we have quite a bit to unpack here. But what we want to do is, we want to kind of test to see if the proportions are what we would expect, or if the data, fit kind of our expected proportions or not. And so the null hypothesis in this case, we would write something like this. We would write, given that an elderly Chinese woman dies within 1 week of the Harvest Moon Festival, if people can't prolong their life or anything like that, we would say she's equally likely to die before the festival or after the festival, right? So basically, we're looking at a 2-week span. We're looking at 1 week before the festival and 1 week after. And so we're saying, if we look at all the people who die within this 2-week span, we would expect about half of them to be during week 1 and half of them to be during week 2, right? That should just be kind of the case. If you looked at, any 2 weeks across the calendar, just randomly choose 2 weeks and you look at how many people died in those 2 weeks, you'd expect there to be approximately equal in the first week as the second week, okay? And so we would say, you know, the probability of dying after the festival would be 0.5. The probability of dying before the festival would be 0.5. That would be the null hypothesis. The alternative, now we are going to use a directional hypothesis. And we're going to say, you know, we don't know quite how it works, but we have a suspicion that these people are somehow able to hold on to life until after the festival. And therefore, that means they are more likely to die after the festival than they are to die before the festival. And so our alternative here, we would use a greater than sign. Probability of dying after the festival is greater than 0.5 versus the probability of dying before the festival will be less than 0.5, okay? And we can write a directional hypothesis because there's only two categories, which means if we want the dying after a festival to be greater than 5, it means the other category has to be less than 0.5. Or again, if you have more than two categories, it's not possible to kind of fully allocate out which proportions should be greater or less. So according to our data, we observed 33 people who died before the festival and 70 people who died after the festival. Okay, so we have a total of 103 people who died within 1 week of the festival. Okay, and so if the null hypothesis were true, the count that we would expect would be 103 divided by 2, 51.5 before, and 51.5 after. Okay, and it's fine that your expected counts have a decimal point. Okay, that's totally fine. Of course, your observed counts will only be whole numbers, but your expected numbers, they're just the product of n times p, and in a lot of cases you'll get decimal values, so it's no issue. All right, so we're going to do observed minus expected, and you know I have them written out here. You know I can put them up here as well. Oops. Okay, so again, if we do observed and expected, you know, we got 51.5, 51.5, 33, 70. This is before and after. And so our chi-squared value is going to be 33 minus 51.5 quantity squared divided by 51.5. And 70 minus 51.5 squared divided by 51.5. Now, interestingly enough, whenever you have 1 degree of freedom, the numerators all end up being the same. The denominators, not necessarily. In our case, the denominators are the same, but 33 minus 51.5, where did my calculator go? So if I do this 33 minus 51.5, and I decide to square this number, I get 342.25. Divided by 51.5 plus 342.25 minus 51.5, because, you know, they have to add up, right? So if I do 70 minus 51.5, I'm going to get the same thing, and I square it, I'm going to get the same thing, okay? 342.25. Okay, and then I take that and I divide by 51.5. I get 6.645. Plus 6.645. And I get 13.29, okay? So this is my chi-squared value. Okay, so I've got chi-squared is 13.29, and we have the degrees of freedom is number of categories minus 1. So I've got 1 degree of freedom because I basically have before and after. Those are my two categories. 1 degree of freedom. Okay, so what we will do is we will go to the table, 1 degree of freedom. We're looking at 13 point something, 13.29. That's in between these two column headings. And again, when we have a directional alternative, we're going to take our column headings and divide by 2. So my tail area tail area is between 0.001 and 0.0001, and my p-value is half. Okay, so that's going to be between, so the p-value is between 0.0005 and 0.00005. Really small values. So 5 10,000ths and 5 100,000ths. Okay. So really tiny values, we would likely reject. We would reject the null hypothesis, and we have evidence. Basically, we have evidence that they're not equally likely to die before or after, that perhaps something is going on. Okay, so our p-values between these two numbers, and we would reject the null hypothesis, and we would say something like, our data provides evidence that if an elderly Chinese woman dies within 1 week of the festival, she's more likely to die in the week after the festival than in the week before. Now, does this mean something? I don't know, right? I don't know how it works, and statistics makes no attempt at trying to explain the mechanism of how this works. All we're doing in statistics is saying, it's very unlikely to be the result of random chance, right? Random chance, sure, if you're expecting half to be before and half to be after, sometimes because of randomness, you get a few more before and a few more after, or just the opposite, you get a few less before and a few more after. Okay, that could happen because of random chance. What we're getting is 33 before and 70 after, and that cannot be explained by random chance, is what we're saying here. We're saying that for that to happen by random chance, it only happens between, like less than 5 and 10,000 times. So it's this very, very rare case. It happens less than 1 in 1,000, less than 5 in 10,000 times. And so, so what does that mean? Well, I don't know. It just means these Chinese women are more likely to die after the week after the festival than the weekend before, if we already know that they're going to die within a week of the festival. Okay, so it's kind of I thought it was an interesting outcome and a clever experimental design, and a nice use of the chi-squared test, which we just covered here. All right. Any questions on any of this stuff so far? All right, let me go ahead and give you your second view quiz answer. The second view quiz answer is B as in bear. B as in bear, B as in boy, ball, I don't know, B, Bruin, okay? Is our second view quiz answer for today, B. Okay, and now I'm going to go into chapter 10, where we have the chi-squared test for independence. These, I didn't type these slides up. I wrote them out by hand, and I pasted them into your notes, and so they are there. But I'll probably, write some of these things out. Okay, and so the question we have now is, if we look at data with kind of two categorical variables, we have a question: is there an association between the variables, or are the variables independent, right? So if is something happening when these two variables get together, or basically, do they operate independent of each other, right? And so so here's the example that I'm going to use, okay? Is we're going to define people with diabetes as having A1C, blood test levels, an A1C over 6.5. And we're going to say high blood pressure is going to be their systolic blood pressure is over 140. And so the question is, do people with diabetes have an increased incidence rate of having high blood pressure? Now we have to be careful with the way we phrase our question. We don't want to say, does diabetes cause high blood pressure? Does high blood pressure cause diabetes or something like that? We got to be careful about using words like cause, because we cannot reveal that kind of information in some kind of study like this, right? All we can say are, these medical conditions perhaps happen more frequently together, okay? And if it's related to, negative patient outcomes, patients dying and things like that, we might call these comorbidities and things like that. But we're just kind of saying, do these things seem to be happening together? And again, we can't make any kind of cause and effect conclusion here. And it would be rather impossible to try to design an experiment where you can draw a cause and effect conclusion, right? So, as far as setting up an experiment, it's not like you can suddenly cause somebody to develop diabetes or cause somebody to develop high blood pressure. So it's not like a drug where you can randomize and give some people placebo and some people the medical treatment. We're just looking at these medical conditions. So all we can do is look at observational studies. Okay, we can only just gather data, and all we can do is make some kind of thing. And so the phrase we're going to use is there an increased incidence rate? Do people with diabetes, are they, more likely to have high blood pressure than people who don't have diabetes or something like this, okay? And so we're gonna kind of treat both of these variables as being dichotomous, okay? So either you do have diabetes or you don't, or, even more simply, you either have an A1C above 6.5 or you don't, okay? And so, I know some, if you have an A1C of like 6.4, you'd probably be called pre-diabetic or something, and your doctors would encourage you to, start making lifestyle changes and things like that. But we're just going to say either, you're above this number or you're not, and if you have a blood pressure of say 139, your doctors probably will make some recommendations to you, but we're going to say you're either, over 140 or not, or something like that. Okay. And so we're going to say, let's, just for simplicity, I use 400 as the total number of observations here. But we have, this is my completely fictional data that I've completely made up. It's not like based on a real study. We're gonna say we have 400 people. Of those 400 people, 40 people have diabetes, 360 did not, 120 have high blood pressure, 280 do not, and 20, we have 20 in this box, 100 in this box, 20 in this box, and 260 in this box. Okay. All right. And so if you recall, what does it mean for variables to be independent? Okay. So if we said events A and B are independent, we would say something like the probability of A given B is equal to the probability of A given not B, and this is just equal to the probability of A, right? And so this is going to be the formation of our hypotheses, okay? So basically our null hypothesis is going to be that events A and B, whatever we're talking about, are independent, and we're going to basically write out the null hypothesis using this part right here. And so that's what I have here. The null hypothesis is that the two variables are independent, that having high blood pressure is independent of having diabetes, okay? And so we're gonna say the probability of having high blood pressure, given that somebody has diabetes, is gonna be equal to the probability of having high blood pressure, given that someone does not have diabetes. So if they're independent, then whether somebody has diabetes or doesn't have diabetes should not have an effect on whether that person has high blood pressure or not, okay? That's what we're trying to say. We're gonna say, if someone's diabetic or not diabetic, it has no influence on the kind of the incidence rate of high blood pressure. That's what the null hypothesis, okay? And the alternative is that there is some kind of relationship. And here we're going to use a directional alternative, okay? We're gonna have an increased incidence rate, okay? So this indicates direction. We're saying that if somebody has diabetes, that that the incidence rate of having high blood pressure is greater than the incidence rate of having high blood pressure if the person does not have diabetes. Okay, and so this is how we would write our null hypothesis and our alternative hypothesis. Okay, what we can also do, and I didn't put these in the notes, but we could also also valid would be to check for probability of diabetes given high blood pressure. Is that equal to probability of diabetes given not high blood pressure? Okay, but, and this is important, do not do this. Don't do probability of high blood pressure given diabetes. Is that equal to the probability of not high blood pressure given diabetes, or something like this, okay? This part and this part, they need to be the same. You can't, it's, you know, it's probability of A given B versus A given not B, okay? You can't change up this from A to not A or something like that. So don't do that. But we'll just leave this like this, okay? All right, so this is what we're gonna do. And so now the question is, what would our expected counts be, okay? And so I'm gonna go ahead and write this out. And so what we have is, so I have a total of 400 people. I think I have 40, and I think these are the numbers from the margins, okay? So first I'm gonna kind of copy values in the margins of the tables. All right, and so this is high blood pressure, and this is not high. And this will be people with diabetes, and we say no diabetes. All right, and so the question is, what do we expect goes here, okay? What is the expected count if they are independent? So if we're expecting the two things to be independent, what would we expect to go in this spot right here, okay? Well, what we would do is we would say, okay, if things are independent, okay, if A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B, okay? And so another way we can kind of think of this is we can say, okay, well, what's the probability of diabetes according to my table? Well, I would expect 40 out of 400, I would expect around 10% of patients to have diabetes, okay? And if they're independent and I have a total of 120 people with high blood pressure, then I would expect, if they're independent, so just if I have a group of 120 people and the probability of having diabetes is just 10%, out of those, how many should have diabetes? Well, 10% out of 120. So I would just kind of do 10% times 120, and I would get 12. Okay. Another way we can think of this is we could say, okay, well, probability of diabetes is 10 out of 20. Probability of having high blood pressure would be 120 out of 400 or 30%. Okay. And so the probability of having both, if I do 10 times 30, we would expect around 3% total, right? So probability of both should be 0.1 times 0.3. So around 3%. Okay. And 3% of 400, 3% out of 400 is also going to be 12. Okay. So I'm going to put 12 right here. Symbolically, or if we wanted to generalize into kind of formulas, we can just say, all right, well, how did I get this number? I took the grand total 400 and then multiplied it by the probability of diabetes, 10%, times the probability of high blood pressure, 30%. Okay, so this is the grand total times 10% times 30%, or, and if we break down the probability of diabetes as just kind of this column total, 40 divided by 400, and the probability of having high blood pressure as the row total over the grand total, 120 over 400, okay, we get the same values. 400 times 40 over 400 times 120 over 400, we get 12 there as well. Or just more generally, we can just kind of use a shortcut formula and say this is the column total 40 times the row total 120 divided by the grand total of 400. All of these things will give us the same answer of 12, right? Is that okay? How I got 12 right here? I hope so. Okay, and so that's what we would expect. If the null hypothesis were true, if these two variables were independent, we would expect to get 12 in this expected count cell, okay? All right, and so actually once I write this number 12 down, everything else kind of just gets locked in, okay? So I think we had 360 because, well, not I think, we did. 40 plus 360 adds to 400. And then in order for 120 plus something to be 400, this has to be 280, okay? And once you have this number 12 in the table, okay, then everything, you only have to calculate it for one cell because everything else just gets determined, right? Because whatever number here goes, it has to be 12 plus something adds to 120. So there's only one possibility. It has to be 108 because 12 plus 108 has to be 120. And if I have 12 here, then I have to put 28 here in order for these two things to add up to 40, okay? 12 plus 28 add up to 40. And likewise, 28 plus something has to be 280, or 108 plus something has to be 360, okay? And so there's only one possible answer, and that's going to be 252, right? Because if I try to put any other number here, if I try to change any of these other numbers, then the row total or the column totals will no longer work out, right? So we're going to copy the values from the margins. And so what we mean by the margins is basically you copy the row totals and your total columns. Copy the values in the margins or the totals. Okay, we'll ignore the inner cells. So these are going to be my expected counts. Okay. Expected counts if the null hypothesis were true, okay? Meaning the variables are independent. So this is what I would expect to get if my variables are independent. I would expect to get 12, 108, 28, and 252. Okay, and so that's what I have here, all right? So I've got 12, 108, 28, and 252. And I kind of filled this out and I said, once you enter 12 into the top left corner, the other three cells can be used just by finding the row and column totals, okay? And this illustrates the fact that once I put one number in and the other threes were kind of locked in, this illustrates something. And if somebody says, well, how many degrees of freedom does a 2 by 2 table have? A 2 by 2 table has only 1 degree of freedom. 1 degree of freedom. Okay, and that's that's illustrated by the fact that as soon as I put one number in, the other three numbers basically had no freedom to be anything else, right? That first number you put in, we could really put in anything from 0 to 20. Okay, so this first number has, quote, a little bit of, quote, freedom. But then once you've determined that number, the other three numbers, have no freedom. So a 2 by 2 table has only 1 degree of freedom. And we can kind of generalize this to any kind of larger table. In our class, just because the process is exactly the same, but the calculations just get way more tedious. But you can have a larger table, say, if you might have 3 categories and 4 categories or something like that, right? You can have a 3 by 4 table, right? So you can say, is there a connection between, say, hair color and eye color or something like that, right? And how many hair colors are there? I don't know how many hair colors you might want to say, but let's say you're going to list off 4 different hair colors, and maybe you'll list off 6 different eye colors. I don't know how many eye colors there are, but in that case, you would have a huge table, 5 columns for hair colors, 6 rows for eye color, and you would have kind of 30 cells, right? You would have 30 cells to kind of figure out. And so in that case, you have a lot more degrees of freedom. You'd actually have to figure out you'd have to figure out 20 of those values. And then once you figure out, 20 of the values, then the remaining 10 will kind of get locked in, I believe. But you're going to have R minus 1 by K minus 1 degrees of freedom. Okay, the number of rows minus 1 and the number of columns, K minus 1. For a 2 by 2 table, it's 2 minus 1, which is 1, and times 2 minus 1, which is 1. So you're going to have a 1 by 1 or 1 degree of freedom. So for a 2 by 2 table, there's only 1 degree of freedom. But for a larger table, you're going to have R minus 1 times K minus 1 degrees of freedom. The process is going to be the same. It's just more tedious. So, as far as our class goes, we'll keep it simple. We'll just keep it to be 2 by 2 tables, 1 degree of freedom. Okay, and so once we have this is my observed data. I observed 20 people having high blood pressure and diabetes, 100 people having high blood pressure and no diabetes, 20 people with diabetes and no high blood pressure, and 260 people, no diabetes, no high blood pressure, okay? This is how the distribution of 400 people. If the null hypothesis were true, I would have expected these values, okay? And so I showed you the process to get the expected values if the null hypothesis were true. All right, and so now we have the observed counts, we have the expected counts, and now we can calculate the chi-squared statistic. So our chi-squared statistic, again, is going to be the sum of the observed minus the expected squared divided by expected, okay? And what we're going to do is we're going to sum all of the internal cells, okay? All four internal cells of the 2 by 2 table, okay? Now, a common mistake, and I'm not quite sure, but I see this frequently on people's quizzes and things like that, is students will not do all 4 cells. They will maybe just do the 2 in the top row, and then they'll stop, okay? So so a common mistake is not doing all 4 cells, not adding all 4 cells. All right, and I'm not quite sure why, but sometimes students will just stop after doing 2 of the cells or something. All right, so we're going to go do this for all 4 internal cells. We're going to do observed. So I'm going to just start in the top left corner. It doesn't matter where you start, but you just have to do all 4 of them. Observed minus what I expected. We're going to square that difference. Divide by what I expected. We're going to go to the next cell. I observed 100. I expected 108. We're going to square that difference. Divide by what I expected. I observed 20. I expected 28. And again, anytime you have 1 degree of freedom, the numerator is going to be the same for all of these things. So you can all see that the numerator is going to be either 8 or -8 squared. So numerator is going to be 64 in all cases. I observed the last case, I got 260. I expected 252. We're going to square that difference. And we're going to divide by what we expected, okay? But just because the numerator is the same for all 4 cells, the expected value is different, okay, for all 4 cells. So sometimes students will just take one thing and multiply it by 4. That's not going to work out, okay? But here I get 20 minus 12, which is 8 squared. So I'm going to have 64 over 12. And then we're going to have 64 over 108. And then I'm going to have 64 over 28. And I'm going to have 64 divided by 252. All right, so let's go ahead and add this up. So we got 64 over 12 plus 64 over 108 plus 64 divided by 28 plus 64 over 252. I hope I did this correctly. I'm getting a chi-squared value of 8.466. Yeah, that is. So this is my chi-squared value, and my degrees of freedom is equal to 1. How do we feel about the calculation of our test statistic? Okay, all right, thank you. Thank you for that thumbs up. All right, so we have that, okay? Yes, I wrote these common mistakes, not adding all 4 cells, and or using observed counts or the same values for all denominators. Yeah, so that, oh yeah, that's another thing. You always divide by the expected number in the denominator, not the observed. So sometimes students will use the observed, or yeah, sometimes students will use the same number for all the denominators. Those are things that I encountered. But yeah, the most common one though is not adding all 4 cells. Students will sometimes just do like the first 2 and then stop. And then your chi-squared value just ends up being like way smaller than what it needs to be. All right, so anyway, I've got chi-squared value, 8.466. I've got 1 degree of freedom. So we're gonna go to our chi-squared table like we've been doing. We look at 1 degree of freedom. I'm looking up 8.466. So my p-value, or my tail area, is between these 2 columns. 8.466 is between 6.63 and 10.83. And so therefore my tail area is also between these 2 values, between 0.01 and 0.001. Okay, and if we go back a few slides, we say, well, what kind of alternative did we have? We have a directional alternative. We have a directional alternative, which means we're going to take our column values, 8.466, and we're going to divide by 2, right? So we say the directional p-values are found by dividing the column headings in half. That's what it says right here. So you just read your table carefully. And a lot of these will say, you know, these are for non-directional alternatives. So we're gonna divide by 2, right? So the tail area is between 0.01 and 0.001. Our alternative hypothesis is directional, okay? And our data do align with the direction. Our data do show that we have a greater proportion of people having high blood pressure if they're diabetic than if they don't have diabetes. And so we're going to take this, divide by 2 to get our p-value, and we get a p-value that's between 1/2 of 1% and basically 1/20th of 1%, okay? So basically less than 1/2 of 1%, between 0.005 and 0.0005, so this really small value. And so if we have a significance level of 5%, our p-value is going to be less than alpha, and we reject the null hypothesis. And our conclusion would be that our data provide evidence that people with diabetes have a higher incidence rate of high blood pressure than those who do not have diabetes. All right. We feel good? Okay, thank you again. Yes, thank you for your, all right, great. Let me go ahead and give you your last view quiz answer, and we'll just call it a day early here, okay? That, believe it or not, that covers chapters 9 and 10, in the textbook. The textbook, maybe goes into a little bit more detail in a couple other sections, but that's pretty much the main part of chapters 9 and 10. You're looking at categorical data. You have the goodness of fit test to see if data fit and observe expected proportions. And then you have the chi-squared test for independence to see if there's kind of any interaction between two categorical variables. All right, so your last view quiz answer for the day is A. A as in apple. A as in apple is your last view quiz answer for the day. Okay, we'll end there. Have a good weekend, you guys. As always, expect to see a kind of a quiz show up on Sunday, and that'll be due Monday evening. And other than that, have a good night, have a good weekend, and we'll see you guys on Tuesday.